2 days ago, we introduced the concept of a vector and a scalar and put 3 terms to go with it: distance, position, and displacement. You guys have mastered those, I think. We wrote a quiz on that today, and you guys have done very well on that quiz. You guys know what the difference between distance, position, and displacement are. Yesterday, we defined 2 more terms: speed and velocity. Speed is how fast something moves. Velocity, the rate of change of position. We introduced 2 new equations yesterday, really 1 equation with 2 different versions, 2 different, slightly different forms of it. First one was the equation for average speed. Speed, how fast something goes, is distance over time. Velocity, which is the rate of change of position, is the rate of change of position over time, or displacement over time. What units is delta D typically in? Not always. Okay, a lot of the problems that we did for our worksheet, in fact, many of us didn't put it in these units. But what's the standard unit for delta T for distance? Dom? Meters. Good. And for time? Seconds. Could we go kilometers for unit for distance? Sure, a lot of times we could. There are times when we can't. I'll tell you when you can't. Okay. For the time being, we can use whatever we want. The standard, though, is meters and seconds. A lot of times you're given a distance, you're given a time, just divide the 2, solve for what you're looking for. What if you're not? What if you're given a time and you're not given a total distance? Maybe you walked 10 meters one way, maybe you walked another 30 meters in the same direction, then maybe you walked 50 meters in the opposite direction. The total distance traveled there is what we need. The total distance would be 10 plus 30 plus 50 is equal to 90 meters. Divide that distance by the time. Not one of them, but the total distance by the time. Same thing for the displacement. Add them up. Just make sure you pay attention to negatives when something is going in the opposite direction. Right? So it's total distance, total displacement, which you may be given, or you may have to add up numbers that you're given in order to find. All right, we had our worksheet. You've already taken a look at the answers here. We know that we're going over number 6. I think that's the only one to go over. But if anybody has any others, at some point, just raise your hand and we can go over whatever you want. 6 says a car travels east at 90 kilometers per hour and for 10 minutes, and then travels at 100 kilometers per hour west for 30 minutes. What's the average speed? What's the average velocity? There's a key word in there, a very important word in that sentence, in that problem. It's the word then. Travels at this speed for 10 minutes, and then it does something else. The word then separates a problem for us basically into 2 problems, 2 questions. We have, in question number 6, a phase A, or you could call it a phase 1, where you have a velocity of 90 kilometers per hour, and you have a time of 10 minutes, or 0.16667 hours. In stage B, right after stage A, then you have stage B, a different problem, where you have a velocity of negative 100 kilometers per hour and a time of 30 minutes, or 0.50 hours. We want to find the average speed and the average velocity. Now, average speed is distance over time. What's the distance here? Over the last 24 hours, I've seen a number of you working on this question. A number of you have asked me a question about this. That's great. Okay, that's what I'm here for. If you're having trouble determining what the distance is, then ask me, and I'll help you. Lots of people said the distance here is 190. Is that right? You can't add speeds together to get a distance. Simple as that. The only thing you can add together to get a distance are distances. Let's get the distance traveled in each of these stages. In fact, let's go a step further. Let's get the displacement in each of these stages. If we take that equation v equals d over t and rearrange it, solve for d, the t goes up by multiplying, solve for d, becomes d is equal to v times t. V is 90 kilometers per hour. Multiply that by 0.1667 hours gives me a total distance traveled, or total displacement, of 15 kilometers to the east. Now, that's the first stage. That's before something else happens. That's before the word then. Then we have our second stage. We're calling it stage B. The displacement during that stage is also v times t, but this time v is negative 100 kilometers per hour. And t is 0.50 hours. Gives me a distance or a displacement of negative 50 kilometers. Now what? We said we want to find the average velocity for the entire trip. We've just found the displacement for the first stage and the displacement for the second stage. What do we do with those two displacements? What do we do with them? Olivia, what are we going to do with those? Add them up. Now, when we're looking for speed, we're not going to pay attention to the direction of the displacement, right? We're going to say 15 plus 50 is equal to 65 kilometers. We don't want the displacement for the first one. We want the distance. The time interval there is 0.6667 hours. We do the math there. 65 divided by 0.667 gives me 97 kilometers per hour. Can anybody explain this to me? A lot of times what we want to do in a question like this, although I didn't see any of you doing this, okay, a lot of times what people will do is say, oh, you want to find the average speed? 90 plus 100 divided by 2. Average them. Add them up, divide by 2. Gives me 95. Halfway in between 90 and 100. Why is my answer here closer to 100 than it is to 90? Why is it on the one side of 95, Hugh? Good. Traveled at 90 kilometers per hour for 10 minutes. Traveled at 100 kilometers per hour for 30 minutes. It's going to be closer to 100. How would you get an average speed that was exactly 95, exactly halfway in between? Michael? Good. Wouldn't matter what that time was. Okay. Well, it would matter what the time was to get the numbers that we got, but bottom line is the average would be halfway in between the two velocities, regardless of what the times were. All right, let's take a look at the average velocity now. Velocity is displacement over time. The displacement is 15 plus 50, 65. How about 15 plus negative 50, which is negative 35 kilometers? And the total time is still 0.6667 hours. Hey, answer this one for me. When I added the displacements, I had to pay attention to the negative. I had to put in negative 50. When I added the times, I didn't. I made them both positive. Why? If it's going to the south, or going to the west, I should say in this question, shouldn't they both be negative? The displacement and the time? Why isn't the time negative here? West, why isn't it negative? Good. Time's a scalar. There is no such thing as a negative time. There's a negative displacement because it's a vector, but not a time. So negative 35 divided by 0.667 gives me negative 52 kilometers per hour. All right, we're going to shift gears a little bit here. Over the last 2 days of class, the only 2 days that we've had, we've talked about vectors and scalars, distance, position, time. And then we've moved a little bit forward, okay, a little bit harder, speed and velocity, along with a couple of quizzes that went along with that. Today we're going to shift gears and talk about graphs. In Physics 20, there are two types of graphs, two main kinds of graphs that you'll see. The first one is called the position time graph, and the second one is called the velocity time graph. We're going to focus on position time graphs today. Notice the title of these graphs, position time, or you might call it position versus time. The first word in the title, in this case position, is always the responding variable. Do you guys remember from Science 9, Science 10 what the responding variable is? You manipulate one variable in an experiment. One variable will change because of that. The manipulated variable is what you change. The responding variable is the one that changes because of that. The responding variable should always be listed first in the title of the graph, and it should always appear on the y-axis of the graph. So, if you're ever asked a question, given a graph, what's the responding variable? Look at the y-axis, look at the title. Okay, it should be on the y-axis, and it should be the first variable listed in the title. Position time. Time is our manipulated variable. Manipulated variable always is listed second in your title. And it always appears on the x-axis of your graph. That's going to become important for us as we start doing experiments and have to plot graphs. Now, the first thing that I want to do here is focus on shapes. In other words, what does each graph of different shape mean? Forget about calculations or numbers or interpreting it in terms of numbers or reading off of it or whatever. Just look at what the shape means. I got 5 examples of position time graphs here, all with different shapes. We're going to go through these and identify what they mean. I don't want you to try to think back to your Science 10 or whenever you did these last and remember what each of these shapes means. I want you to figure it out. For every single one of these 5 graphs up here, figure out what they mean. First one, position time graph, straight line. What do you think that would mean? Yep. Go ahead. First one. Okay. As the time increases, position increases. In other words, it's moving, right? If the position increases, it's moving. That's correct. Could we be a little bit more specific with that? Right, because it's a straight line, it's moving at a constant rate. So time increases, position increases, it's moving. Because it's a straight line, it's moving at a constant rate. So in other words, this first one is representative of a constant velocity. Second one. Yep. How do you know that? Perfect answer. The position is not moving. The position is not changing. Look, the position here is, I don't know, whatever the y-axis value is there. The position here is exactly the same. The position here is exactly the same. If the position is not changing, it's got to be stopped. So we're going to say not moving or stopped. You could say, although this would be kind of odd, you could say this. It's a constant velocity of what value? It's a constant velocity of 0. Yeah, it's kind of an odd way to say it, but a constant velocity of 0, that's constant, right? Constantly 0. Same thing as saying it's stopped. We're not moving. Third one. Third one here. It's sloped downwards, but it's still a straight line. Anybody for this one? Mike, is your hand up there? Okay. Okay. Okay, so it's going back towards where it started. Can you be a bit more specific, though? Anybody help him out? It is going back towards where it started, but it's doing it at a, no, it's not slowing down. It's still a constant velocity because it's still a straight line. Anytime you have a straight line, it's constant, right? Constant sum. So this is a constant velocity. We might call it a constant negative velocity. What does that mean exactly? Hey, let's say I drive to Calgary. Constant speed. I'm not speeding up, not slowing down. It's a perfect highway. Nobody's out there. I'm just driving at a constant speed of 100 kilometers per hour the entire way into Calgary. Then I stop when I get to Calgary. I come back to Okotoks. My velocity on the way to Calgary is a positive velocity. My velocity on the way back to Okotoks is a negative velocity, not because my car is in reverse going back towards Okotoks, although it could be. That'd be kind of a difficult way to get back home to Okotoks. It could be. The negative velocity doesn't mean that, though. The negative velocity means that I'm going back, as Michael said, to where I started. So I'm going in the negative direction, but not backwards. I'm going in the negative direction, probably forwards, just back to where I started. Fourth graph. First time we got a curved line here. Yep, Dom. It's accelerating, it's speeding up. You can see that if the velocity is represented by the slope of the graph over there, you can see that the velocity is increasing. It's getting bigger and bigger and bigger. So it must be accelerating. Or you could say speeding up if you wanted. And finally, the last one. It's doing what? It looks like going, oh wait, the slope is decreasing. What's happening to the velocity if the slope is decreasing? Good, it's slowing down. We might say it's slowing down. We might say it's decelerating. We might say it has a negative acceleration. I'd accept any of those as answers. Oh, one more. Forgot to put this one up here. Let's see what you can do with this one. Position, time. Oh, this is an ugly shape. You ready for this? Two straight lines. Anybody have an answer for that one? Good answer. Velocity goes up, but time is going backwards. What does that mean? You're going back in time. It's a trick question, and you guys got it right away. The last class took about 5 minutes to get this. Time's going backwards. You can't do that, right? It's a trick question. You can't go back in time. Don't bother copying this one down. You'll never be asked that on a test. I just want to see if you guys can interpret it. That's a good answer. Okay, that's a good answer. How about this one? This one's also a little bit of a trick. You don't need to copy this one down either. Position time graph looks like this. What's happening? Yep. You stop time. You're changing position. You're moving, but time has stopped, and that's impossible as well, obviously, right? Okay, I like those two graphs, not because they mean anything. They don't really mean anything in the real world, but in order to get them correct, you do have to understand graphs, not just remember what somebody's told you about graphs before. Okay, so we've gone through the basic shapes of graphs, what different graphs or different shapes of those graphs mean. Now let's take a look at how to find something from a graph, how to get something off of a graph, read it or calculate it off of a graph. We're going to label this graph position and time. Let's draw a nice straight line right here. We're going to find 4 things off of this graph, or at least I'm going to show you how to find 4 things. We don't have any numbers, so we can't actually obtain values from this graph, but we can look at the methods that we might use. Finding the position on a position time graph. Let me tell you this. If you ever want to find something that appears on the y-axis of a graph, if you want to find position from a position time graph, velocity from a velocity time graph, force from a force time graph, go up and over. What do I mean by that? If I want to find the position at this moment in time, I'll go up and over and read that position. If I want to find the position at this moment in time, I'll go up and over and I'll read the position there. Now the displacement, how do we define displacement again? The change in what? Good, the change in position. Do we not just find position by going up and over? Displacement is the final position minus the initial position. In other words, it's up and over times 2. Let's go up and over to get a position. Let's go up and over to get another position. And then let's subtract the 2. That gives me the displacement. What's the equation for velocity? We've only got one, right? What's the equation that we've learned for velocity? V equals, good, displacement over time. Look at what we just got. We just got displacement. So in the first question, we go up and over to get position. In the second question, we use position to get displacement. In the third question, we use displacement to get velocity. So one question kind of leads into the next question. Take the displacement that you get by going up and over, subtracting the 2, and then just divide it by whatever the time is. So in this case, example that I have on the board here, up and over, take this displacement and divide it by this time to get the velocity. Finally, the instantaneous velocity. Sometimes some of the trouble we have in physics, especially on a quiz or a test, is not so much the physics part of it, it's the reading comprehension part of it. We see a term like instantaneous, and we don't know what that means. Instantaneous velocity. Does anybody want to take a stab at what that might mean? The instantaneous velocity. It's kind of an ugly word. Yeah. Good. It's the velocity, not average. It's not the velocity over a trip or over an interval. It's the velocity rate now. Or it could be the velocity rate now. The velocity at one moment, one given moment in time, at one instant in time. Now, here's the nice thing about instantaneous velocity, in one of these graphs at least, a straight line graph. If you've got the velocity of this entire interval right here, because it's constant, then you've automatically got the instantaneous velocity anywhere along that line. If I calculated the average velocity of that blue line to be 6 meters per second, then the velocity at any point along that blue line must be 6 meters per second. So we're just going to write a little sentence here. If you have a straight line, then the instantaneous velocity will equal the average velocity. So question 1 led us to question number 2, right? Position led us to displacement. Question 2 led us to 3. Displacement led us to velocity. And then 3 leads us to 4. Average velocity leads us to instantaneous velocity, as long as it's a straight line. You haven't seen anything that's not a straight line yet. You will. Okay, but for now, as long as you have the average velocity of that straight line, it's the same as the instantaneous velocity. Good? All right, let's do an example with some real numbers, and then we'll give you 4 questions to work on yourself, and that'll be it for the day. Here's the question on the front of your worksheet. Let's do this as our example here. We've got a position time graph. Hey, what's our manipulated variable here? Quick, manipulated variable is? Time. Good. What's our responding variable? Position. Good. We know that because first variable in our title is always going to be responding variable, and the y-axis of our graph is always going to be responding variable as well. All right, we got that out of the way. Got a straight line, slopes downward. What does this mean, by the way? What's the shape of this graph represent? Straight line sloping downwards. It is constant velocity, but, Dom, no, it's not accelerating negatively. Good, it's a constant negative velocity. So it's going at a constant velocity, but it's going backwards in the negative direction. Not in reverse, not the car in reverse, but back from Calgary towards Okotoks, or back towards where we started from, right, Michael? All right. What's the position of the object of the graph at 10 seconds? How do we find position? Oh, look, up and over. So let's go to 10 seconds here. Let's go to 10 seconds, and let's go up and over from 10 seconds. Up, over, looks like the position at 10 seconds is 30 meters. Now we'll define east as positive, and that'll save us from having to write the word east in every single time we do one of these questions. This is 30 meters, right? Just up and over, simple as that. Now displacement between 0 and 10 seconds. Well, we need final position minus initial position. df minus di. df is 30 meters. We just found that. di at 0 seconds, the position is 80 meters. So my displacement here will be negative 50 meters, or you could have said 50 meters to the west. The average velocity between 0 and 10 seconds. We did that too. Hey, velocity was displacement over time. We just found the displacement. The displacement was negative 50 meters. Well, the time is 10 seconds, so the velocity would be negative 5.0 meters per second, or you could have said 5.0 to the west. Oh, here's a toughie. Where is it? The instantaneous velocity, the velocity at one moment in time. The velocity at 2 seconds, right here. Let's go back to this, our notes for a second. Find the instantaneous velocity of a position time graph. If it's a straight line, do we have a straight line there? Yeah, we do. If we have a straight line, then the instantaneous velocity equals the average velocity. Well, the average was negative 5. So the instantaneous velocity at 2 seconds must be negative 5 meters per second. Same thing for number 5. It's a straight line. The instantaneous equals the average. It's going to be negative 5 meters per second. You guys feel comfortable with that? Comfortable enough to have 4 questions to work on now? Okay, take a look at the back side of that worksheet and work on these 4 questions. You got about 15 minutes. Okay, good chance you can finish all 4 of these questions in class here. If not, finish them up for homework. Ask me questions. Please ask me questions if you're struggling with any of these. All right, let's get at it.